All right, next lesson, electrolytic cells. So you're going to know the difference between galvanic cells, which you've been studying, and electrolytic cells, which are kind of their opposite. And you will be able to determine the quantities of electrolytic products given cell chemistry and current supplied. So let's get to it. The difference. Galvanic cells. These are cells where spontaneous chemical reactions are used to supply electrical energy. Batteries. So electrolytic cells or electrolysis is the opposite process where you're actually, by supplying electrical energy, driving a non-spontaneous reaction, usually to make something that you want. Now, this is especially useful for processes that end up being thermodynamically highly unfavorable because electricity is a good way to get a lot of energy into something. And I'm just going to talk about this in the context of probably the biggest industrial example of it, and that is the refining of aluminum metal. Now, aluminum is kind of an interesting thing. You know, it's by far the most common metallic element in the Earth's crust, but it is not in the form of aluminum metal. Aluminum metal is actually very highly reactive, especially with oxygen. And so when you dig aluminum out of the ground, it's in the form of the mineral bauxite, which is a form of aluminum oxide with some waters of hydration entrenched in it. And so the idea is that you're going to use electrical energy to reduce the aluminum ions to aluminum metal. And this can be done with this reaction right here. So aluminum oxide, you can have 2 moles of aluminum oxide, can be converted into 6 moles of aluminum metal and 3 moles of oxygen gas. So let's work out some numbers here. So we can make a couple of estimations here. So the aluminum standard reduction potential, if you look it up, and that is a whopping negative 1.66 volts. Now it's going to be paired with, somehow we need to turn these oxide ions into elemental oxygen O2 gas. And the way that you do that is with this reaction here. And this is the oxidation reaction here. But if you look this up in the standard reduction potentials, so this is the reduction of oxygen in water to elemental oxygen, giving you protons and 4 electrons. And this is the oxidation potential, and that clocks in at negative 1.23 volts. So the standard cell potential here is going to be negative 2.89 volts, and so that means that this is, under standard conditions at least, this is not a process that wants to happen at all. But if you supplied energy equivalent to this or greater, you could drive the process, you could drive the process in this direction and convert the bauxite into aluminum metal. So then you need to think about how you would actually pull this off. Could you just dissolve aluminum oxide? And the answer is no. It is not a soluble thing. And furthermore, at those reduction potentials, you would actually break down, if you wanted to, even if you could dissolve it in water, at the potential that you need to work at to oxidize, to reduce the aluminum, you would actually break down the water first and never get to the aluminum. But it does turn out that aluminum oxide dissolves quite nicely, or dissociates quite nicely, into this stuff here, sodium aluminum hexafluoride. This is something called cryolite, and this is actually an ionic compound as well. It's got 3 sodiums as the cation, and this is a complex ion composed of an aluminum plus 3 ion complexed with 4 fluoride ions, giving it an overall negative 3 charge. So 3 plus 1's, 1 negative 3. That's called cryolite. And this you can actually make a solution of this cryolite and the aluminum oxide at temperatures that are still fairly hot, but still achievable on a large industrial scale. So then the next question is exactly how much energy, or more specifically, how much current would you need to supply? Now remember that a current is a measure of the flow of electrons per unit time. So current is generally the SI units of current is an ampere, which is one coulomb per second. All right, so now let's think about this and get the units right. All right, so we know that we require, to make 1 mole of aluminum metal, we need 1 mole of aluminum ions and 3 moles of electrons. All right, so this is our conversion factor, so to speak. And the current is proportional, and the current you need is going to be proportional to the number of moles of electrons. The current that you supply, I should say, is proportional to the number of moles of electrons that you will create, and again proportional to the amount of aluminum that you create. All right, so here's our half reaction here. So current, again, it's equal to a charge divided by the period of time over which that charge was transferred. The SI unit is 1 ampere, or 1 amp as it's frequently called, and is equal to 1 coulomb of charge per second. Now, the charge on an electron is not 1 coulomb, it is much, much less than that. But again, we're still not talking about individual electrons, we probably want to talk about moles of electrons as well. And this is where the Faraday constant comes in. And the Faraday constant of 96,500 coulombs is equal to, by design, the charge of 1 mole of electrons. All right, so, and here is our question. So you're going to supply current in our cryolite aluminum soup, specifically 521 amps for 8 hours. And then the question is, how much aluminum metal will you produce from that, in that 8-hour shift? And just to put this number, this current in perspective, probably the largest electricity consuming appliance in your house is a refrigerated air system, if you have one. And those things, when they are running full bore, will draw about 25 amps. So this is 20 times that amount, and this is actually a fairly small production scale. Actually, it's almost a boutique level scale. But again, so we're talking about 20 times the current in 8 hours, and 20 times the current that a household air conditioner or central air system draws. Okay, so how do we set this up? So first, let's get our time units consistent. Let's convert things to seconds. So we have 8 hours. 1 hour is 3,600 seconds, so that corresponds to about 2,800 or 28,800 seconds. And now we can figure out how many moles of electrons you supplied at 521 amps for that 8 hours. So 521 amps is equal to 521 coulombs per second. This was done for 2.88 times 10 to the 4th seconds. And you know that each 96,500 coulombs corresponds to 1 mole of electrons. And so, to the dimensional analysis, seconds cancel, coulombs cancel, we have moles of electrons. So that current delivered for 8 hours supplies 155 moles of electrons. And so the next question is, how many moles, how much aluminum does that give us? Well, we know that, get the pointer back here. We have 155 moles of electrons that was delivered. Each 3 moles of electrons will give us 1 mole of aluminum. So that means that we have produced, at that 8-hour production shift, 51.8 moles of aluminum. And the mass, again, aluminum clocks in at 27 grams of aluminum per mole. So that is a mind-whopping 1,400 grams of aluminum. 1.4 kilograms. That is a couple of pounds. So I want to get on my environmental soapbox here. The electricity needed to refine aluminum from the ore for a few pounds of it is the same thing as running a house, is the same amount of electricity as roughly 20 household central or refrigerated airs for 8 hours. That's a lot. This is why, and for aluminum, for a couple of reasons, the aluminum has to be refined this way. And so and this is just to convert it to the aluminum. You still have to purify it, do a few more things to it. And it must be done in an electrolytic cell. So this is why not every country, in that matter, produces a lot of aluminum. Those that tend to have pretty high market shares are those where electricity is cheap, where there's a lot of hydroelectric power available. And this is a lot of energy, and I will say that it takes much, much, much less energy to remelt and recycle aluminum metal that's already been made, rather than to make new aluminum from the ground. So while aluminum on Earth is not a particularly precious resource, making the aluminum metal requires a lot of energy, so recycle the damn cans. All right, next up, how batteries work in detail, in different kinds of batteries. So stay tuned.